Welcome, big day. We're going to continue to fill in our knowledge of derivatives for every type of function that you learned about in a pre-calculus class or in the past. So next up, something I'm sure you've been waiting for, trigonometric functions. Those are our old friends sine, cosine, tangent, cotangent, cosecant, and secant. These six right here. We will worry about inverse trig functions later. Before we get going, a quick note. In this class, always radians, never degrees. Turns out our nice formulas for derivatives of trig functions don't work if you have degrees. You end up getting weird multiples of pi over 180 flying around every time you take a derivative if you're in degrees. So if you've never had a good reason why we should worry about radians or why we should use radians, calculus is maybe the best reason because of how nice it makes things if we stay in radians. Okay, I'm guessing that you probably need a quick reminder, not like a full-fledged review, but a quick reminder of some of our trig function properties. So sine and cosine are usually our base functions that we work with, but tangent can be thought of as sine over cosine. I'm going to leave out my of x's and my of thetas or whatever other variable you want to use for right now, make our lives easier. Cotangent is just 1 over that. So cotangent is just, it's 1 over tangent, also known as cosine over sine. Okay, this is freaking unusable. Also known as cosine over sine. Cosecant is 1 over sine, and secant is 1 over cosine. Why would they name them like that? Historical reasons. I'm sorry. I know that you want to think that cosecant is 1 over cosine, but it's not. So that means that really if we learn sine and cosine, we can figure out the rest just by using things like the quotient rule. And I'm sure also that a lot of you first started learning trig functions using right triangles. One of the reasons why trigonometry is tough for people is because it's useful, and because it's useful, there's lots of different ways of thinking about it. And when there's lots of different ways of thinking about the same thing, students get confused. So ever so quickly, if we had some angle on a triangle we cared about, then on a right triangle, that is, then on the opposite side, we'd call that opposite. The adjacent side we call the adjacent, and then the hypotenuse is always just the hypotenuse. And so we also learned that sine is opposite over hypotenuse. It's that ratio of that right triangle. We learned that tangent is opposite over adjacent. We learned that cosine is adjacent over hypotenuse. We learned that cotangent is adjacent over opposite. We learned that cosecant, 1 over sine, just means flip that sign, so this would be hypotenuse over opposite. I know those O's look like zeros, but they're not. It's just kind of a shorthand to remind you of something you hopefully learned in the past. And cosine is hypotenuse over adjacent. So really, from this, if you just know these three ratios, you can kind of figure out the others because they are just flipping something from the past. Okay, probably the better way to think about these, though, is on the unit circle, which we'll talk about in a second. A fun fact that we learned already is that all of these functions are continuous on their domains, which is great. The domain of sine and cosine is everywhere. But the rest of these have something in the denominator. So to figure out the domain, we need to figure out when is that denominator 0. So for tangent, the denominator is cosine. We need to figure out when is cosine 0. And the right triangle method is not very good for telling us this. So usually when I'm thinking about these things for quick reference, usually I am thinking about the unit circle. And on the unit circle, you think about having some angle here. We think about it's a unit circle, so the radius is always 1. And then secretly in there is this right triangle, which means that opposite over adjacent is opposite over 1. Sorry, opposite over hypotenuse is opposite over 1. Adjacent over hypotenuse is the adjacent over 1. And so the denominator goes away. which means, okay, what is this x value? The x value is just how wide this base is. So the adjacent over the hypotenuse of 1, that is just my cosine value. So the x value is the cosine. The y value is the opposite over 1, and that's just sine of that little hidden triangle there, which tells us that the point has the coordinates cosine of theta, sine of theta. Again, I'm leaving out my thetas because I'm being sloppy, but I think it helps you kind of see what's going on if I don't have x's and thetas everywhere. Okay, so what this means then is that as I travel around my circle in the counterclockwise direction, that's the positive direction, I start here and I go around like that, which means that this is a 0. How far is it around this unit circle? Well, that is half of the circumference, so this would be a pi over here. So when I'm saying when is cosine 0, I'm saying when is the x value on that unit circle 0. Well, that looks like the x value would be 0 here, or the x value would be 0 here. So cosine of half of pi is pi over 2. But of course also at negative pi over 2, if I go back the other way, but also at way down here is 3 pi over 2. Okay, and so really if you notice the pattern here is that we start at the top, we go to the bottom, we go to the top, we go to the bottom. It's changing by pi, by halfway around that circle, and that's why tangent has those asymptotes with distances of pi. It is a period of pi, and normally what you just draw is that first one in between negative pi over 2 and pi over 2. Similarly, sine of x is 0. That's going to happen when my y value is 0. When is my y value 0? It looks like that happens over at 0, but also at pi, but also at 2 pi, but also at 3 pi, and also going backwards the other way at negative pi. Okay, all these functions are periodic, so any answers are going to come up over and over again. Right, but that's just going to happen whenever I am at 0 or pi. So you definitely, even if you don't memorize everything else, you quickly need to know, all right, when are they 0? When are they 1? It would be nice if you also knew the other common ones, pi over 3, pi over 4, pi over 6. But certainly where are they 0 and 1 needs to be mighty fast. Okay, whew, that was a quick review. I wanted to at least remind you of that much so that we can sketch these things a little easier as well. So that when we think about sine of x, we think about something going around in a circle, starting at 0, getting bigger, and then getting smaller, and then getting smaller, and then getting bigger. This is one of the reasons why sines and cosines work, is because they describe circular motion so well. They also describe ratios involving angles so well, and much of the real world involves circles and ratios of angles. So let's see if we can plot this real quick. Sine of x. We're first just going to start with sine of x, and then we'll figure out what the derivative is. So sine of x, we just said on that unit circle, it starts at a 0, and it looks like it reaches its max at that fun value of pi over 2. So we'll call this a 1 up here. Okay. And then it looks like it goes down to a negative, it goes down to 0 at pi, and it goes down to negative 1 at pi over 3. And back to 0 at 2 pi. And we could go the other way as well. Okay. And if you know your sine waves, you know that it should make a nice smooth curve. We could include all those root 3 over 2s and those 1/2s as well. But let's see if I can draw something a little bit smooth here. Up. My attempt at drawing a sine wave. Not the worst thing ever. It's a pretty decent sine wave. Of course, it repeats over and over and over again. All right. So let's use this to see if we can try to draw a quick version of what its derivative should look like. So its derivative, well, I like to start with when is it 0? looks like I'm going to have a horizontal tangent line, or a slope of 0, maybe there, maybe also right there. It's nice periodic fashion. Okay, so let's go ahead and include those as zeros in this new graph of its derivative. If it's a 0, that's where it's going to touch the x-axis. Okay, let's see if we can figure out where it's at a maximum. By the way, just to include it up here, I didn't include it on the y-scale, but this is a 1 and this is a -1 because it's on a unit circle. The biggest and smallest it can get is a 1 and a -1. Okay, so where is the derivative at a maximum? That is going to be where this graph is the steepest. Okay, and it looks like it's going to be steepest right where it's crossing the x-axis. That's where it kind of hits that inflection point, that place where it changes its curvature. So it's going to be steepest kind of there every time it crosses the y-axis. So it looks like it's going to have a peak at 0, and that's a positive derivative. It's going to have a peak, or rather a minimum. So maximum is 0, looks like a minimum. It's steep downwardly at pi, and then another positive peak at 2 pi, and it should be periodic, right? If sine is periodic, then its derivative should also be periodic, so it should be going through some kind of a similar pattern. So let's see if I can fill this in here a little bit best I can. Something like that. I'll finish this off. And got a little shaky there. Okay. Pretend that's a nice smooth curve. Great, it should look something like that. But this looks mighty familiar. What function is this that is periodic with a period of 2 pi, and it starts at 1? I'm going to go ahead and tell you it has an amplitude of 1 as well. What function is this? Do you know? I know. This function is actually an old friend. This is cosine of x. Okay, this is maybe a poor proof of that, but drawing is a good way to kind of convince yourself, oh yeah, that makes sense, that sine of x is steepest at 0, and cosine of x is highest at 0. And they're both a derivative of 2 pi, they both go down and up and down and up. Makes a lot of sense. We will prove this in the future. Very, very cool. Okay, so then what's the derivative of cosine of x? Let's see if we can play the same game. Where is it 0? Well, that's where my tangent line is 0. So let's add those points. That would be at 0 here and at pi. And when is it going to be steepest? It looks similarly like it's going to be steepest when it's crossing the x-axis. So if I include those points, it looks like it's at a peak at -pi/2. It's at another peak or maximum at 3 pi/2. Maybe you can try to fill this in yourself. It's at a minimum at pi/2, and I can try to connect these dots again. Oops, I got this. I was off by a point there. And then right back down to 0. Nice. That looks familiar. What I'd love for it to be a sine, but it's clearly not sine. It's related to sine. What is the relationship between sine and this graph? It's going through 0 again, if I kind of hit that 0, right? But it seems to be flipped the other way. How could I possibly flip a function the other way? What would flip it upside down? Oh, I know. We're just going to put a negative out in front. So the derivative of cosine of x is just negative sine of x. Amazing. Amazing. Oh, that is so nice. And of course, what we're going to do the rest of this lesson is use that like crazy. So put those in your notes, see what else you can figure out. In fact, let's go ahead and write them down officially. That the derivative of sine of x is cosine of x. You'll often see a lot of thetas for angles. So I'm going to write this again just using a theta, but there really is no difference between these two. And the derivative of cosine of x is negative sine of x. And of course, if I use a theta, that really doesn't change anything. Negative sine of theta. Let's put a box around that because that is important. Boom. Boom. All right, next time we will go ahead and do some examples. You can feel free to try those on your own if you want. All right, till the next video.